Good afternoon, everyone. Did you enjoy your runs? Yeah, my name is DJ, and I'm CTO of Lightscale. Today, I'm going to introduce Kroma that we are building to solve the blockchain scalability problem. Kroma is a Rollup-based Ethereum layer 2. Yeah, there are two main streams in Rollups, Optimistic Rollup and ZK Rollup. Optimistic Rollups are more widely used because they are EVM compatible, but they have late finality. In opposite, ZK Rollups have faster finality, but they are EVM incompatible. And this makes it harder for dev developers to join the ecosystem. Oh, I'm sorry. Yeah, I'm sorry, there are some problems. Yeah, to solve this problem, several teams are building zkEVM. But it is not enough for now because it still takes too much time to generate proofs. So our team, Lightscale, is building a unique Rollup solution to overcome these limitations. To build Kroma, we adopted various best practices from existing projects such as Optimism, Arbitrum, and Scroll. Optimism is one of the widely used optimistic Rollups. Recently, they have been developing Optimism Bedrock. It has inspired our team so much. So we took many things from Optimism Bedrock: model architecture, Rollup, and derivation processing, and P2P. These make it possible to bring lower fees, higher throughput, and faster response. Arbitrum's interactive fault proof is very efficient. We adapted it to our ZK fault proof mechanism. Scroll is contributing to the zkEVM so much in conjunction with Ethereum Foundation. We basically started with their zkEVM. Based on those foundations, we added our original ideas. At first, we use ZK proof to Rollups in a way that is practical. We begin with an Optimistic Rollup where fault proof is implemented with zkEVM. We call this as ZK fault proof. At this stage, ZK proof is only used to resolve dispute challenges because it's too slow to generate proofs for all blocks. After optimizing ZK proof generation, we will move to EVM, equivalent to ZK Rollups. We designed a smooth transition mechanism. Decentralization always matters, so we have been designing and implementing Kroma, where validators and proposals can be easily decentralized. So I will explain some interesting parts of Kroma, such as basic Rollup protocol, challenge system, transition mechanism, and decentralization. And also, I will present current status of Kroma and future roadmap. OK, let's see the basic Rollup protocol. Many of them were from the Optimism Bedrock, and we modified several parts for adopting challenge system and ZK proof. I'm not sure whether you know that Optimism doesn't have some challenge systems for now. OK, there are three types of participants in Kroma network: user, proposer, and validator. Users can deposit or withdraw transactions on L2 by sending data to a contract on Ethereum mainnet. Users can submit arbitrary transactions to proposers and validators, just like the layer 1. Proposers accept users' off-chain transactions and observe on-chain transactions. Usually, on-chain transactions are deposit events. Proposers consolidate both kinds of transactions into L2 blocks with a specific ordering. Validators drive L2 chain by leading data in L1 chain. They also verify the integrity and also checkpoint. If there is any invalid checkpoint, validators can also submit dispute challenge on the invalid checkpoint. Regarding the network participants, there are some differences between Optimism and Kroma. First of all, I changed the node names like this. I think this matches well to the participants of layer 1. This makes it more natural to reuse L2 components in the similar way of layer 1. In optimism, sequencers not only submit batches, but also checkpoints. On the other hand, in Kroma, proposers just submit batches, and validators submit checkpoints. By changing like this, validators can receive rewards from checkpoint assertion as well as dispute challenges. Consequently, this resolves verifier's dilemma of optimistic rollup. Let's see how L2 blocks are rolled up to L1 by a proposal. L2 blocks are built with L2 transactions from mempool. L2 blocks have some reference to the L1 block so that deposit transactions in the L2 blocks will be properly included in the L2 block later. As shown in this figure, L1 deposits are stored in the first L2 block just after the L1 block. L2 blocks are more frequently created than L1. For now, L2 blocks are created at every 2 seconds. So several L2 blocks are encoded and compressed into a channel. Then the L2 channel is split into channel frames so that each channel frame can be stored in a single L1 transaction. A validator can read channel frames from L1 blocks as well as deposit events. Then the validator can reconstruct channel from this data, and finally L2 blocks can be built from the channel and deposit event read from L1. These processes are managed by multiple components. Just like the L1, the execution engine manages mempool, builds L2 blocks, manages states, and serves RPC requests. The rollup node requests to build a block to the execution engine with the proper payloads. The batcher manages channels and channel frames and submits channel frames to L1 network. A validator also has a rollup node and an execution engine. The rollup node reads frames from L1 blocks and derives L2 blocks. The rollup node uses engine APIs to build the L2 blocks. The execution engine works in the same manner as proposer, except that the execution engine does not build a block from the mempool. This figure shows how Kroma handles user deposits and L2 transactions with these components. The proposal node builds blocks with user deposits and transactions and submits batches into layer 1. The validator node derives blocks from the batches and deposit events. The validator components, the validator component in the validator node gets the latest checkpoint output from the rollup node and submits output to L2 output oracle contract. Outputs are submitted every 1,800 blocks with 2 seconds block time. It is an hour. And output is generated with version type and payload. Same version number means that the structure of the payload is the same. In the current version, a payload is composed of state root, withdrawal storage root, block hash, and next block hash. Output roots are very important because they are used to confirm withdrawals from layer 2 to layer 1. And also, output roots will be used as public inputs for verifying ZK proofs. For a user to withdraw this For a user to withdraw his assets from L2 to L1, the user has to submit a withdrawal initiating transaction to L2 contract first. Then the proposer submits batches with withdrawal transaction data to batch inbox. A validator gets blocks and submits an output that contains withdrawal commitments. The user needs to wait until the block is finalized. After block is finalized, then the user can request to finalize withdrawal to the bridge contract. Bridge contract verifies the transaction with the output root by checking if the withdrawal storage root contains the withdrawal data. If the transaction data is verified, the user finally gets his assets. This figure shows the overall architecture of Kroma without dispute challenging. Currently, we are using modified Go Ethereum as the execution engine. Therefore, built-in peer-to-peer network and transaction pool is used to propagate transactions. The same network is used to propagate submitted blocks and support SnapSync. For the better compression and lower load of cost, the batcher does not submit batches until enough number of blocks are collected. Therefore, in general, there are some unsubmitted blocks in the proposal. Those unsubmitted blocks are called as unsafe blocks. They are propagated through another peer-to-peer network of Rollup nodes. Using those two peer-to-peer networks, execution engine can respond to users' requests with low latency at every node. Until now, validators only act as an asserter. Now let's see how validators act as a challenger. Okay, let's assume there is a faulty output that is provided by another validator, that is an asserter. Basic process to build L2 blocks are the same. Rollup node get the data and call engine APIs. This validate component reads an output from the L2 output oracle and also reads the corresponding local output from the execution engine and compares them. If the assertion output is different from the local output, the validator submits dispute challenge. To resolve the challenge, the validator first needs to find where the difference starts from at a single block level. After finding the block, the validator component requests to generate a ZK proof to the ZK prover. The ZK prover gets execution trace for the block from the execution engine and generates a ZK proof. The validator component submits a proof to the L1 contract. Then the ZK verify contract verifies the proof. If the proof is verified, the challenger wins and gets some rewards. If the proof cannot be verified, the challenger loses, and his staked asset will be transferred to the asserter. Let's see more details about these two parts. When identifying a faulty output, we begin with two checkpoint outputs. The first checkpoint output should be the same to the challenger's local output. Between those 1,800 blocks, there must be an initial block where the challenger's output and the asserter's output are different. The challenger gets to know the initial block position by interacting with the asserter, who submit the faulty checkpoint output. At first, the challenger submits 46 output loops that evenly distributed between these blocks. Then the asserter compares these output to his local outputs and finds the first different output. The asserter submits all the outputs between those blocks. Again, the challenger compares those outputs to his local outputs and finds the earliest different block. Then the challenger generates a proof that shows his local output and finds the earliest, shows his output is valid and submits the proof to the Colosseum contract finally. This figure shows the state transition in the Colosseum contract. The challenger starts a challenge by staking his asset in a checkpoint. Right after staking his asset, the challenger submits output segments, and an asserter should respond to it within a time limit. In most states, there are some time limits so that the challenger process ends within the reasonable time. In the previous example, the faulty block was found with just 2 interactions, but there may be more interactions with different segmentation schemes. Interactions must be an even number so that a challenger can start the interaction and submit a proof after the asserter turn. We tested several segmentation schemes. Among them, we choose this 9585 segmentation scheme because it consumed small gas with a reasonable number of interactions. Actually, we inherit the zkEVM of Ethereum Foundation. Scroll also uses the same code base with some modifications. To reduce the proving time, we use ZK try instead of Merkle-Patricia try. We use Poseidon hash instead of Kekak, and ZK try to compute the path to the account or storage slot. We added additional specs for layer 2, such as L2 deposits and lot of gas fee processing. Yeah, this shows the circuit structure. There is a super circuit that embeds many circuits designed for the specific purposes. Execution trace is a private input. Oh, I'm sorry. And there are some public inputs that are accessible from L1 blocks. With these private and public inputs, we can obtain a block proof. Actually, circuits are not fully implemented yet. We will have fully implemented and verified the zkEVM before launching our public mainnet. Yeah, now we have the full architecture. There are some additional components to use ZK proof in Optimistic Rollup and ZK Rollup as well. Yeah, this Colosseum contract manages challenge process. And these are for the ZK proof. Kroma have ZK-friendly data structure and hashing schemes from the initial stage. Therefore, even though we start with Optimistic Rollup, we can move to ZK Rollup without any heavy migration process. Okay, now let's see how we can move to ZK Rollup. In the ZK Rollup, once a block is created, a prover will generate a proof for the block. While blocks are created at every 2 seconds, generating a proof usually takes much more time. So multiple provers need to generate proofs in parallel at the same time. So I think the most important part for ZK Rollup is the proving pipeline. In this figure, except the first proof, others include the previous proof in their proofs. Then the checkpoint can be verified using only one proof. Since multiple provers generate proofs at the same time, resources might be used redundantly to generate the same proof. Currently, we are designing Kroma for ZK Rollup to utilize resources efficiently using a consensus algorithm such as POW without a centralized coordinator. For example, the created proofs will be propagated among provers through the P2P networks of the Rollup nodes. Yeah, many of you wonder why we do not start with ZK Rollup, even though we already have designed these. In Kroma, L2 block time is 2 seconds. Though the actual proving time takes more than 30 minutes for now, let's assume proof generation time is 30 minutes for simplicity. Then, about 1,000 of machines should be pipelined at the same time. With proper machines, we will consume more than $1 million a month only for operating provers. Let's see the top 2 L2 platforms' recent revenue. Then, as you see here, ZK Rollups are not feasible for now. Therefore, we need to optimize much more for moving to ZK Rollup. If we reduce the proving time sufficiently, we are going to operate proving network. In this figure from the block BI plus K, a checkpoint output is verified with a proof. After challenge period, the block BI is finalized. Then after the block BI checkpoints that verified by ZK proofs bring the instant finality of blocks. Then the network can be considered as a ZK Rollup without any further changes. Of course, there must be more issues that we have to address. This is the basic idea how we can transit from the Optimistic Rollup to ZK Rollup. Okay, now let's talk about decentralization of Kroma. There are two types of decentralization in Kroma: validator decentralization and proposer decentralization. We designed a reward system that motivates validators to join Kroma. It serves verifies dilemma, and hence we expect to have a stable network with a sufficient number of validators. Currently, most rollups operate single sequence or a proposer. In this situation, users should trust that the sequencer is honest and there is no censorship and MEV abuse. We are going to adapt proposer builder separation using trusted execution environment. This will support strong censorship resistance and block MEV abuse. Currently, we are focusing more on validator decentralization. It's based on staking model. So validators need to stake assets to do validation. Validators can get rewards from the two types of successful validation activities: checkpoint assertion and dispute challenges. The source of the rewards is fee margin. Users pay three types of fees in the Kroma. Base fee and the priority tip are the same as the layer 1, and lot of fee is defined only for layer 2. Lot of fee is used to submit transaction batches into L1, and hence the proposer receives it. I'm sorry. And those two are usually considered as L2 execution fee, and some portion R is accumulated into validator reward vault. R will be determined dynamically according to the network situation. Usually, there are 24x7 waiting output submissions. Just remind the checkpoints are submitted every hour, and we have 7 days challenge period. So if the checkpoint output is finalized after the challenge period, the validator receives some portion of the reward vault. To participate in the validation process, a validator should stake a certain amount of bond. High bond makes validation less profitable. Low bond may lead to abuse. Required bond is computed with the balance of validator reward vault, the number of the waiting output submissions, and the staking factor. A validator stakes the amount of this and receives the amount of this after 7 days challenge period. Usually, there must be 24x7 waiting output, and hence validator APR can be estimated simply like this equation. This means that validation APL as well as the staking amount can be controlled by the alpha. Alpha will be determined by the number of active validators. So if there is not enough validators, then alpha will be set by a small value. Then the expected APL will be higher, and this motivates more validators to join the network. If there are too many validators, then the expected APL may not be enough to some of the validators. Then they will leave the network. So the proper number of validators can be naturally controlled with alpha. We need to escape from a situation where a few validators get the most rewards. So there will be a randomly selected validator that has a priority to submit a checkpoint. If the selected validator does not submit a checkpoint on time, then the reward gets smaller. If the selected validator missed the turn, then other validators have the chance. If all other validators miss the chance, then the trusted validator that are operated by the Lightscale will submit the output. Through this, we can escape from missing checkpoint outputs. We set the required bond for a challenge as the same to the required bond for the assertion of the target output. If the challenger succeeded in a dispute challenge, it gets assertor's bond. If the challenger loses, it loses the bond. This will prevent from the abuse. If the challenger does not start the challenge on time, then it will get less reward. Even if there is a fault and no validator submit the challenge, then trusted validator submits the challenge and get rewards. Through this decentralization scheme, we can keep Kroma network more secure and stable. We have finished the POC last year. We launched the first our testnet last month as an optimistic rollup. We are currently operating single proposer and single validator. Testnet fully supports P2P propagation. We are currently working on integrating decentralized validation model. It will be integrated in the next month. TSS-based Security Council will be integrated in June. We are also preparing to deploy several dApps such as swap, DeFi, and NFTs. After massive testing, we are going to launch the mainnet within third quarter this year. I hope that we have an EVM-Equivalent ZK Rollup in the next year. This is the British screenshot of the testnet. And this is the block explorer of our testnet built with the block scout. And you can visit Kroma network. This is the Kroma hub. You can access all the resources from the Kroma hub. Thank you for your attention. Do you have any question? Have any question? Yes.
Yeah, Consensus SYS has a ZK rollup already, right?
Yes.
How do you compare this Kroma with Consensus ZK rollup?
Yeah, I already mentioned that ZK rollup needs some kind of high computing power. So I think the cost is the problem, and also the slow proof generation time is the problem. So currently, we checked several ZK rollup like ZK Sync Era and Polygon zkEVM, and the Scroll and Tycho and other stuff, but they didn't complete the implementation. So actually, I think it takes some time to be ready for the actual real use case users. Actually, there are some ZK Sync Era already have mainnet, but I didn't see all the zkEVM specs in their implementation. So I'm not sure whether it's already completed the implemented zkEVM. Yeah.
Hi, thank you for a great presentation. My question is, so do you envision a future where all the optimistic rollups will be transferring to ZK rollups?
Yes.
Or would Arbitrum and Optimism still exist, let's say, a few years from now?
I'm sorry?
Would all the optimistic rollups would transition to ZK rollups, or would they coexist?
Yeah, we already discussed within our team, but I think there are various ways to be some practical rollups. So optimistic rollup, currently the optimistic rollup dominates the market, and ZK rollup continuously increasing the TVL in the L2. But actually, I don't know whether they change it to the ZK rollup or already they have some kind of visions. Optimism have. Actually, we already use the Optimism the architecture. So, and they mentioned that in their architecture, they easily move to the ZK rollup. Maybe it's similar to our approaches. So, all the people and all the teams have similar visions, but The problem is that whether they can have that kind of practical zkEVM or some kind of optimization of the ZK Rollup. That's my idea. Any other questions? Yeah, I think there is no other questions. So thank you. Thank you for your attention.